We already have complaints about new slide compression technique used. So it's 12, and I think we should start. Can everybody hear us, see us?
Yes, I can hear.
Over here, you guys
Thank
fine.
you. So welcome everybody to IETF 111 Routing Working Group meeting, first meeting. We'll have another meeting tomorrow, and we are happy to see you as always. So Injan and myself, and let's start with share status update. Not well. If you're unfamiliar with terms not well, please go read all the BCPs and RFCs in here. Everything you disclose to IETF becomes property at IETF. Please be aware of IETF rules. We've got a routing working group specific IPR disclosure process. We call IPR twice, once before working group adoption, once before working group last call. Unless we receive all the responses from all authors and contributors, documents won't progress. Please be aware. To repeat our charter here, and we've been using it really successfully. You'll see a lot of interesting stuff this IETF. We facilitate process of innovation. We propose home to some proposals that could potentially go into other working group or progress in routing working group, or perhaps develop a both. From administration perspective, we are going to review the agenda, review all the working group documents available, and links here are to show you where it is, and thanks to Linda for taking the notes. So we are going to describe what I just discussed. Then we'll have Fred Templing spending 60 minutes talking about our Omni and BGP-based mobile routing system. We will also discuss further steps on it. Then a Service 6 midpoint presentation, and 2 more drafts that are exactly in scope of routing working group charter, new technologies, new proposals, and potentially development of such technologies in routing. For Thursday, we'll have again new technologies, and I'm very excited to bring discussion about self-healing network flow label. This work started in 2015 with Linux patches, and now being deployed in a number of hyperscaler data centers. Really interesting technology being discussed in 6man at some point in time. So I really wanted just to bring it into routing so people get aware of what's going on here and how it's being used. We didn't publish any new documents since 110. Nothing has been adopted. So existing working group document, the routing working group policy model, we are waiting for the new document, and practically it's really ready and it's final review opportunity for you. QS model update has been published to address young doctor review. We need more reviews, and Injan agreed to be the shepherd, so some work expected here. And then RIB extended. We are looking for a shepherd to progress the document. BGP peak, we are in process of reviewing all the updates and comments. Segment routing, TILFA, we've got great work by Stuart, and we are still expecting to address reviews that are going to be proposed by Routing Directorate and other reviews. And ATN BGP is going to be presented now, as well as egress protection draft. There's a number of individual drafts that are covered in this IETF. We would also like to do some review of what's going on and perhaps rejuvenate some discussions before 112. There's a number of architectural documents that been dormant for quite some time. So if not clean up, we would like authors to take a look at what's been done and perhaps have another discussion on the list. And this is all for chairs. Engine, anything to add?
I think we're good.
I see Alvaro.
Yeah.
In the queue. Please go ahead.
Hey guys, thank you. Alvaro Rtgwg, Routing AD. I just want to really quickly thank Chris Bowers, who, as you all know, stepped down as chair a few weeks ago. And thank you for all his work. He is here today. He's still shepherding some of the documents as well. And welcome, of course, Yingsen as the new chair of Rtgwg. As you notice with the slides and everything, the working group is not missing a beat. So thank you, both of you, for your work. And that's it. Thank you so much.
I feel ashamed I didn't do it myself. Chris, thank you so much. It has been a pleasure working with you, and we'll absolutely continue working together. And Ingen, you're no stranger to this work, so a bit late, but welcome, and thank you for stepping up.
Yeah. I'm honored to get this opportunity to serve the community. So if there is anything Jeff and I can help, or you see anything that we can do better, just let us know. Thank you.
Okay, now it's time to move to presentations.
Yeah, so Fred is the next presentation because he has some animation in his slides, so he will be share his screen.
Okay, thank you, Yingsen. I'll go ahead and get my screen started and my video started. Hopefully the video comes through okay. Let me try sharing my screen. Okay, so far so good. Is the screen share now visible?
Yes,
it is.
Yeah, good to go.
Thank you. So today I'm going to be talking about 3 documents that are interrelated but separate documents. I'm going to be talking about a simple BGP-based routing service for the Aeronautical Telecommunications Network, and I'll also be talking about Aero and Omni, and we'll get further into those in the next charts. So the first document, a simple BGP-based mobile routing system for the Aeronautical Telecommunications Network, is a document working group item of the ART Routing Working Group. It is a BGP-based spanning tree overlay, actually, configured over one or more internetworking segments based on a non-broadcast multiple access or NBMA interface model. And it uses IPv6 unique local addresses for navigating the spanning tree. The autonomous system border routers of each segment are in a hub and spokes arrangement with peering between the adjacent segments hubs. The IETF Routing Working Group has had this as a working group item since August 30th, 2018, and it has been coordinated with the International Civil Aviation Organization Aeronautical Telecommunications Network. And this work, we believe, is ready for IETF Routing Working Group last call. The next document, known as Automatic Extended Route Optimization, provides route optimization extensions that can establish shortcuts over the spanning tree I referred to earlier to avoid strict spanning tree paths. It provides for mobility, multi-link, multi-hop support based on an agile hub and spokes arrangement of clients associated with proxy servers. You see a pointer to the document there, and we believe the work is now ready for IETF adoption. And then finally, transmission of IP packets over overlay multi-link network interfaces, or OMNI interfaces. The OMNI interface is a single NBMA network interface that is exposed to the IP layer and offers a fixed 9 KB MTU to the IP layer. However, it's configured as an overlay over potentially multiple underlying physical or virtual interfaces that may have heterogeneous MTUs that may be different sized than 9 KB. Within the interface, a sublayer known as the Omni adaptation layer provides a minimum mid-layer encapsulation that maps the IP layer to the underlying interfaces. And again, this pointed to the document, and we believe the work is ready for IETF adoption. So how does this look like in a typical deployment scenario? So here we have Aero and Omni in a single internetwork case where we have clients that are represented by these airplanes, as you see around the periphery, that connect to access network subnetworks via one or more data links. You see that some of the clients have just a single data link, others have multiple. The subnetworks then connect to the inner network through devices known as proxy servers that are at the subnetwork edges, and they can act as either IPv6 routers or IPv6 neighbor discovery proxies. And then internal to the inner network, we have bridges, our nodes that establish the spanning tree over one or more inner networks, and again use an IPv6 unique local addresses in the Omni adaptation layer as an encapsulation sublayer that sees the spanning tree as a layer 2 service, the same as a bridge campus LAN would do. So in other words, the original IP packets generated by clients or nodes on their downstream attached networks would travel over this spanning tree as a single IP hop, even though there's multiple hops going on at a layer below IP, which is where I say this is a L2 service. So in the bigger picture view, we might have arbitrarily many internetwork segments joined as a non-broadcast multiple access link. We would do a form of segment routing over the concatenated internetworks using the OAL forwarding service. Some examples of internetworking segments could include the IPv4 public internet, the IPv6 public internet, corporate enterprise networks, cellular operator networks, aviation networks, and many other examples. Now, note on this that we show the clients here in these figures as connecting only to single subnetworks or internetworks. However, it's possible that clients may connect to multiple different internetworks. One example that occurs is within the aviation domain, where we have aviation navigation service provider networks such as AirInc, CETA, and Inmarsat, where a client could connect to all three of these different internetworks and still receive the Aero and Omni big picture view that we're showing here. Now, in terms of the Omni interface, the overlay multi-link network interface, all Aero Omni clients, proxy servers, and bridges configure Omni interfaces, which is the node's connection to the Omni link. Client Omni interfaces are configured over multiple underlying interfaces, and they connect end user networks. So if you see the diagram in the upper left here, we show the Omni interface as being a layer below IP, but a layer above the L2 underlying interfaces. So we're showing here IF1, IF2, and so forth through IFN. The Omni interface uses IPv6 encapsulation. I'm sorry, I've got to hide a pop-up window here. There we go. To span the entire concatenated internetworking path in a single NBMA L3 hop, so that all Aero and Omni nodes are neighbors on the link. So if you look at the diagram on the left here, or the right here, you see the Aero proxy servers, clients, and bridges all appearing as neighbors on a link, the Omni link. And this link is manifested through NBMA encapsulation over one or more internetworks. Now, in terms of Aero Omni client underlying interfaces, there may be various different ways in which a client could connect to its first hop proxy server. First is the direct connect or point-to-point model, where the client's underlying interface, for example, an Ethernet or a Wi-Fi link, connects directly to the proxy service at layer 2 over a point-to-point media without traversing any layer 3 hops. A second example is a VPN interface, where the client's underlying interface uses network layer security to establish a virtual link to a proxy server over one or more layer 3 hops. Then is the access network model, where the client's underlying interface connects to a secure access network, for example, an enterprise network, a cellular operator network, etc., where there are layer 2 and layer 1 security provisions on the path to the proxy server, but then the proxy server connects to an external internetwork. And then finally, the internetwork model, in which the client's underlying interface connects directly to an external internetwork, for example, over a coffee house public Wi-Fi or a hotel public Wi-Fi. In this case, the proxy server may be one or more layer 3 hops away from the client's point of connection, and the client may also be located behind one or several network address translators. Now, clients may have diverse underlying interface types, which may connect to multiple distinct internetworks as opposed to all via the same internetwork. For example, an INET interface could connect to the public internet. An ANET interface could connect to a cellular operator network. A direct interface could connect to a dedicated enterprise network proxy server, and etc. And the client can utilize all of these underlying interfaces according to traffic selector attributes that we'll talk about later. So in terms of encapsulation and segment routing, the Omni interface is going to insert mid-layer encapsulations between the IP layer and the underlying interfaces. And it's going to use minimal encapsulation with effective header and compression so that we don't have excessive encapsulation overhead. So if you look at the diagram on the upper left, you see that the network layer, which is where original IP packets come from, injects the packets into the Omni interface, which is a virtual sublayer nexus that's configured over multiple underlying interfaces. It may apply OAL encapsulation, potentially fragmentation. It might include a UDP encapsulation if the packet needs to traverse a public internet. It then would include IP encapsulation, decapsulation, and layer 2 encapsulation, decapsulation for transmission over the underlying interfaces. Now, the OAL mid-layer segment routing is used as necessary to traverse the spanning tree over disjoint internetwork segments, as shown in the right-hand diagram. Here we have segments A, B, C, etc., where the bridges of each segment peer with one another, and we use segment routing to traverse the different segments between a source and destination. But then we also apply route optimization to avoid strict spanning tree paths whenever possible. Now, in terms of Arrow and Omni addressing, each client is going to be advertising an IP global unicast address, also known as a mobile network prefix or an MNP, to its downstream attached end user networks and or its onboard end system applications. So for example, 2001 DB812:/64 is an example of an IPv6 mobile network prefix based on an IPv6 global unicast address. So again, end user applications use mobile network prefix addresses as the source and destination addresses of the original IP packets they send. Now then, each Arrow and Omni node configures an IPv6 link local address for use in IPv6 neighbor discovery messaging. Clients configure a mobile network prefix link local address. So for example, for the mobile network prefix 2001 DB8:1:2, the MNPLLA is FE80 followed by a string of zeros, then ending with 2001 DB812. So you see that the global unique address prefix, the 2001 DB812, becomes the suffix of the link local address. That's what's known as the Arrow address format. Proxies and servers and bridges instead configure an administrative link local address where the 32 least significant bits are configured according to the segment routing topology, node numbering, and subnetworking. For example, for the segment routing topology subnet 2001:1000/24, administrative LLAs within that subnet are assigned as FE80:2001:1001, 2001:1002, 2001:1003, etc. And that's the administrative link local addresses that are assigned to proxy servers and bridges. And then finally, each Arrow and Omni node configures an IPv6 unique local address, where clients, proxy servers, and bridges configure ULAs by concatenating the lower 64 bits of their link local addresses with the OmniLink 64-bit ULA prefix. So for example, if the ULA prefix for the OmniLink was FD00:0102:03:04:05:6, then the MNP LLA taken from the above MNP LLA is shown in that long string we see that begins with FD00/128. And finally, clients, proxy servers, and bridges use ULAs as the OAL header source and destination address. By the way, it's not stated here specifically in the document, but the OLA header is simply an RFC 2473 IPv6 encapsulation header using IPv6 encapsulation. Then finally, Arrow and Omni proxy servers configure IPv4 and/or IPv6 anycast addresses to advertise the OmniLink reachability into access networks. That would allow potential clients that connect to the access networks to send network join IPv6 neighbor discovery messages with an anycast encapsulation destination address to discover the nearest proxy server for the desired OmniLink. So for IPv4, the anycast address that we'll be using is 192.88.99.1. This address was formerly reserved as the 64 relay anycast address, but that use has been deprecated. So what we'll be asking for is the IANA to reclaim that prefix for the use of Arrow and Omni. And then for IPv6, the anycast address is going to be based on the 64 expansion of 192.88.99.1. As you can see, that expansion is 2002:C058:6301, followed by the 64-bit mobile network prefix, followed by a 16-bit link suffix. That address would be broadcast into, well, not broadcast, propagated into the IPv6 routing system of the access network, and any prospective client that wanted to join the OmniLink could send control messages with an encapsulation header that includes that as the destination. And the IPv6 routing system will then convey the messages to the nearest proxy server. Now I want to talk about the ATN BGP routing system. And again, this is the routing working group working document that we're looking for working group last call on. So in this model, we have the proxy servers are simply stub autonomous system border routers, and they peer with bridges as core autonomous system border routers. Bridges use BGP to peer with the bridges of different segments to create a ULA-based spanning tree, which you can see here in the green lines. So with the spanning tree, we have the secured spanning tree is configured over layer 2 security mechanisms using features such as IPsec or WireGuard. And then we also have the unsecured spanning tree, in which there are no layer 2 security provisions. Now, the reason for this, which is not very well called out in these slides, but must be clearly understood, is that we will secure all control messages that traverse the spanning tree. Now, again, IPsec and WireGuard are used in the core network between proxy servers and bridges. In the client to proxy server arrangements, we'll use either the native L2 security features of an access network, or over public internetworks, we'll use HIP messages that provide HIP security so that the client can securely convey its control messages to the proxy server. And then once conveyed securely to the proxy server can convey it across the secure spanning tree to other infrastructure nodes, other bridges and proxy servers. So about the Omni interface and the Omni adaptation layer. So the OAL source is the node that configures an Omni interface that admits an original IP packet. And again, the packets can be up to 9180 bytes, which is the Omni interface MTU. The OAL source encapsulates the original IP packet in an IPv6 header with, again, ULA addresses. It includes a trailing checksum, and then fragments, if necessary, includes INET or access network headers to create carrier packets. And these carrier packets are guaranteed to be small enough to traverse all paths across all potential internetworking segments between the OAL source and the OAL destination. So again, the carrier packets traverse one or more internetworks to the OAL destination, which will securely reassemble, verify the checksum, then forward the original packet to the final destination. This allows the original source to tune packet sizes to achieve optimal performance based on both hard and soft path MTU discovery feedback. And we'll get more into that later. Now, when we apply automatic extended route optimization, we can include these intermediate nodes known as bridges to join different segments together. So in this case, the OIL source and the final destination are in different internetwork segments. The OIL source, again, is going to produce carrier packets, and the OIL destination is going to reassemble, but the intermediate nodes, in other words, bridges, join the network segments in the spanning tree. And this also provides support for global mobility and route optimization, again with dynamic MTU tuning. So the control messages used to establish routing information, to establish these route optimizations I've been referring to, are IPv6 neighbor discovery messages. All IPv6 neighbor discovery message types are used, including router solicitation, router advertisement, neighbor solicitation, neighbor advertisement, and sometimes even redirect. So Arrow and Omni nodes use IPv6 neighbor discovery messages for OmniLink neighbor coordination, and the messages include a new IPv6 neighbor discovery message option type known as the Omni option. The reason for including the Omni option is first to assert protocol conformance. This is to assert to both ends that the Omni protocol is being observed. Secondly is to synchronize identification windows. And then finally to exchange configuration information. And on the right, you see the format of the Omni option. It's in TLV format with a type field that has the type of the option, which is something that we'll have to procure from IANA to identify this as an Omni option. The length provides the length in octa words of the entire option. Prefix length and source target OM index refer to the prefix length of the source address of the message and the underlying interface index used to carry the message. And then you see sequence number, acknowledgement number, flags, and window. You may notice that these are copied exactly from the TCP header because they're used for exactly the same purpose, which is to establish a window of outstanding identification values. And without having this window, it would be impossible to detect spurious carrier packets that should be dropped. But once windows are synchronized, any spurious carrier packets that don't have an in-sequence, in-window sequence number can be dropped. And then finally, the sub-options provide the configuration information. So when a client first joins the network, the clients and proxy servers exchange router solicitation and router advertisement messages either directly or via proxy middle box. So when a client sends an RS message to proxy server A with either all routers multicast or the administrative link local address of A as the destination, proxy server A assumes the router role and returns a unicast router advertisement message while injecting the client's mobile network prefix into the Arrow Omni routing system. This is the ATN BGP routing system that we refer to into the working group document. When a client, however, sends an RS message to proxy server B with the administrative link local address of another proxy server A as the destination, B instead assumes the proxy role and it forwards the RS message to proxy server A, which then returns a unicast router advertisement to the client via proxy server B acting again as a proxy. So then proxy server A becomes the hub, also known as the default router or mobility anchor point, in a hub and spokes arrangement with all other proxy servers B star as the spokes. And the client can later switch to a different hub by sending new router solicitation messages. So what this looks like in terms of a figure, here we have a client that connects through 3 underlying interfaces. Again, this is could be within a single internetwork or across multiple internetworks. The first proxy server that's coordinated with, which is shown in the lower portion of the diagram, becomes the hub proxy server. And again, it will act as an IPv6 router and a mobility anchor point. The remaining proxy servers are instead enlisted in proxy mode, where they forward a proxied version of the router solicitation message to the hub proxy server and act as proxies instead of routers. Now, this is very important because if any one of these proxy servers were to go down, for example, if the hub went down, the client can very quickly select another as the hub and select the remaining proxy servers as proxies to go to the new hub. So once the client has established its presence in the network through coordinating with proxy servers in this way, it can begin setting up route optimizations to talk to peers in the Arrow-Omni network. So the source Arrow-Omni nodes would use neighbor solicitation for address resolution messages and send them into the secured spanning tree to discover the underlying interface configurations for target clients. Once it receives a neighbor advertisement for address resolution, it would then have the underlying interface for the target client that it wants to communicate with. So the secured spanning tree delivers the neighbor solicitation to the target client's hub proxy server, which returns a neighbor advertisement message with multi-link link layer addressing information for the target. Then when the source Arrow-Omni node receives the neighbor advertisement for address resolution, it can select source target underlying interface pairs and send neighbor solicitation for unreachability detection messages to populate forward path state in the nodes on the path to the target. When the target receives the NS of NUD, it returns a neighbor advertisement message of NUD to populate the reverse path state and to confirm that the bidirectional state information has been established. Now, also during this NS-NA of NUD exchange, both send-receive identification windows are established with acceptable carrier packet identification value ranges. Any carrier packets then received with identification out of that range can be safely discarded. So in terms of forwarding then, once we have done this NS-NA of NUD exchange to select the source and target underlying interface pairs, the source is going to use OAL encapsulation and fragmentation to produce carrier packets and forward them into a first hop segment. This is the segment that their local underlying interface is connected to. The segment routing topology, then spanning tree, then traverses any intermediate segments. And then finally, the last hop segment delivers the packets to the target. But forwarding can be based on either the OAL IPv6 addresses, IP address-based forwarding, or a completely new type of forwarding that we call multi-link forwarding vectors that are indexed by multi-link forwarding vector indexes. So let me now speak about the Arrow-Omni multi-link forwarding vectors. The OAL header again includes IPv6 UALA source destination addresses for traditional IPv6-based forwarding of carrier packets over strict spanning tree paths, but this may result in longer paths and more encapsulation overhead than are necessary. So therefore, Arrow-Omni introduced a new forwarding table that is known as the Multi-Link Forwarding Information Base, or the MFIB. The Multi-Link Forwarding Information Base contains multi-link forwarding vectors, and they are identified by unique 32-bit multi-link forwarding vector indexes. So that when an OAL source sends an NS of NUD toward a target, it includes an Omni option with a multi-link forwarding parameters block to establish multi-link forwarding vectors and reverse path B MFVIs in the Arrow nodes, Omni nodes along the path. When the target returns an NA of NUD towards the OAL source, the NA of NUD follows the reverse multi-link forwarding vector path created by the NS and establishes forward path A MFVIs. Once we have the multi-link forwarding vectors and the multi-link forwarding vector indexes populated, then large portions of the OAL header and fragment header can be omitted, and an OAL compressed header can be included instead. And additionally, any unnecessary hops between the source and target can be skipped so that we can avoid strict spanning tree traversal and also provide an effective route optimization. So the multi-link forwarding parameters block is essentially a blank slate that's included by the source that sends the neighbor solicitation message for neighbor unreachability detection. It's an omni option sub-option with type 3. It includes first hop segment and last hop segment parameters with associated forward mode type and segment routing topology codes. The first hop segment and last hop segment parameters include a client, UDP port, and internet address, a proxy server mobility service ID and internet address, and a bridge mobility service ID internet address. It also includes a list of up to 5 AB MFVIs established at each first hop segment, last hop segment path. And then finally, A and B indexes plus a 2-bit job code that tells the proxy servers and bridges in the path what the role of this NS or NA message is in establishing the MFVI state. So when an Arrow Omni node creates an MFV that records the OAL source and destination ULAs and records two 32-bit multi-link forwarding vector indexes. One is a local A, which is for the forward path, and one is a local B, which is for the reverse path MFVI. And it also records any next hop A MFVIs or any previous hop B MFVIs. The local A, B MFVIs must be assured node local unique through the example, a 32-bit random number generation while testing for local uniqueness. But they need not be unique among other Arrow Omni nodes. So to be very clear, MFVIs are not IP addresses. They're not MPLS labels. They're not autonomous system numbers. They're not security parameter indexes or any of that type of thing that is typically seen in internet networking. They're simply unique local 32-bit integers that are node local unique scope. So when an Arrow Omni node processes an NS of NUD message, it creates an MFV, generates a local B MFVI while recording its information in the multi-link forwarding parameters, and then forwards the NS of NUD to the next hop towards the target. And this forwarding is going to be done at a layer 2, by the way. It's not a layer 3, so that the TTL hop limit of the NS is not going to be decremented when it's forwarded. When the next hop Arrow Omni node receives the NS of NUD, it creates a multi-link forwarding vector, caches the previous hop B value, and generates a local B MFVI and forwards as above. Then when finally the final hop Arrow Omni node receives the NS of NUD, it discovers the full map of the previous hop nodes along with the B values for all the previous hop nodes. So then finally, the final hop Arrow Omni node receives the NS of NUD and creates the multi-link forwarding vector, assigns a unique local A MFVI, then generates a neighbor advertisement of NUD and returns it towards the original source by following the reverse chain of B MFVIs created through the NS of NUD. When a previous hop Arrow Omni node receives the NS of NUD, it locates the MFV based on the cached B MFVI, caches the next hop A MFVI, and assigns a unique local A MFVI. And then finally, when the first hop Arrow Omni node receives the NA of NUD, it discovers the full map of next hop nodes along with the A values for all hops on the path to the target. So I want to show, taking this very slowly, how this actually works. So what you see here are all the actors in this scheme. We have the first hop segment client, we have the first hop segment proxy server, the first hop segment bridge. And then we have the segment routing topology spanning tree that could span potentially many segments along the way to the final segment, which is known as the last hop segment. The last hop segment connects to the spanning tree by the last hop segment bridge, then the last hop segment proxy server, and finally the last hop segment client. So what would happen is that the first hop segment client would create a neighbor solicitation message for neighbor unreachability detection, include a multi-link forwarding parameter block, and create a B local value, a B local MFVI value. It would then forward the neighbor solicitation message to its first hop segment proxy server, which would record the B of the previous hop as the B out value, and also create a unique local B in value. And the vector would point backwards towards the first hop segment client, as the previous hop that sent the neighbor solicitation message. And then the first hop segment proxy server forwards the NS to the first hop segment bridge, which does the same thing. Records the B out value, records a pointer to the previous hop, and creates a B in value. The bridge then forwards the neighbor solicitation message into the spanning tree, where it will take strict spanning tree hops using IP address-based forwarding until it arrives at the last hop segment proxy or bridge, which again creates a B out and a vector to the previous hop and a B in value. And that then forwards the neighbor solicitation message to the last hop segment proxy server, and then finally to the last hop segment client. Once the neighbor solicitation message has been received at the last hop segment client, all B values and all vectors that point in the reverse chain toward the original source have been established. So what happens next is that the last hop segment client will then create a neighbor advertisement message and create an A local value that again is a multi-link forwarding vector index, uniquely chosen. It's got to be unique within that local node. For the neighbor advertisement message according to the B path and the reverse path, with each node in the path again creating its A local value and a pointer to the next hop node until the neighbor advertisement message traverses the spanning tree and returns to the first hop segment, where the bridge, proxy server, and finally the first hop segment client record their A values. And so now what we have in the path is that we have B values in the reverse path, A values in the forward path, and this provides us all the information that we need for the multi-link forwarding vector forwarding that I was referring to before. So after the AB MFVIs have been established, OAL peers can begin sending carrier packets while omitting significant portions of the OAL header, fragment header, and the compressed routing header 32 by using the Omni compressed header type 0 or type 1. The Omni compressed header type 0 or type 1 includes the A or B MFVIs for the next hop arrow Omni node according to the directionality established in the NSNA of nut exchange. For example, the NS source would include A MFVIs, and the NA responder would include B MFVIs since its messages are traversing in the reverse path. When the arrow Omni node receives a carrier packet with an Omni compressed header, it uses the MFVI to locate the MFV, which includes the next previous hop information. The arrow Omni node then rewrites the MFVI value in the OCH header and forwards to the next previous hop. And this MFV-based forwarding is based on a single 32-bit MFVI, and it can be used to avoid strict spanning tree paths, as I'll describe next. So after the MFVIs have been established, OAL peers will exchange additional NS and NA of NUD messages before reachable time expires to keep the soft state alive. If the reachable time expires, the arrow Omni nodes simply garbage collect the MFVIs, and future NSA and NA of NUD exchanges would be needed to reestablish new MFVs. The exact MFVIs from expired MFVs need not be reused when initializing new MFVs. All that required is that the MFVIs are unique within node local scope until their reachable time expires. So since there are 2 to the 32 possible MFVIs, and since the number of MFVIs in use at a given time will likely be much smaller than 2 to the 32, random number generation should produce a unique MFVI after a very small number of attempts, usually only one try. So let's now look at a couple of cases where route optimization can come into play. Here we have a chain where we've established the MFVIs in both the forward and reverse directions between a first hop segment client and a last hop segment client. Now, normally what happens is that the packets will go to each node in the path without skipping any of the nodes. However, that provides more work than is necessary, especially on the proxy servers. And so it would be very useful to have a route optimization that can eliminate unnecessary nodes from the path. So after the route optimization, the first hop segment client can send to the first hop segment bridge while skipping the first hop segment proxy server. And the reason they can do this is because the client and the bridge are within the same segment, which is that they can use encapsulation to talk to each other without having to go through the proxy servers. Now, this is what happens when we have the clients in different spanning tree segments, SRT spanning tree segments. If the clients happen to be in the same segment routing topology segment, then we can have a common bridge that's both the first hop segment and last hop segment bridge. Now, again, before route optimization, we would be going through proxy servers, but after route optimization, the first hop segment client can go to the first hop segment, last hop segment bridge to the last hop segment client without going through proxy servers. And then finally, after client-to-client route optimization, we can have the first hop segment client speaking directly to the last hop segment client without involving any infrastructure elements, neither proxy servers nor bridges. Now, NAT traversal issues. When the source and target client underlying interfaces connect to an open internetwork, there's a very good chance that it may be located behind one or more network address translators. Each client naturally establishes NAT mappings when it performs an RA exchange with its first hop proxy server, but these mappings generally are not viable for client exchanges with other Air-Omni nodes, since the other Air-Omni nodes would not be using the same encapsulation source address and destination addresses as for the proxy server. So when Air-Omni route optimization is applied, the route optimization peer nodes must perform NS of NA NUD and bubble exchanges to establish NAT mappings for itself in the NATs on the path to the client. And these NAT traversal procedures are one and the same as what appears in RFCs 4380 and RFC 6081. So after clients have gone through this route optimization and have gotten the shortest paths possible by avoiding spanning tree paths, they may at a later time change their underlying network connection points, for example, changing their addresses, so that hub proxy servers will announce client state changes, again, based on a mobility-related address change, based on link quality changes, traffic selector changes, and other things that would affect the client's reachability. And they announce these changes by sending unsolicited neighbor advertisement messages to all nodes that it has recently sent a neighbor advertisement for address resolution to. When these nodes receive the UNAs, they update the state information for the client, and that may require them to issue new NS of NA NUD path state exchanges, which is okay because the nodes will be able to track the mobile client even as it moves. The new hub proxy servers send UNAs to inform old proxy servers that the client has departed. So when an old hub proxy server receives an UNA saying that the client has departed, it records the new hub proxy server LLA, withdraws the MNP route, and forwards the UNAs to any nodes that has recently sent an NA to. Now, target nodes can request selective link layer transmissions by sending unsolicited neighbor advertisements to the source with the identifications and orbital fragment numbers of any missing fragments. When the source node receives these UNAs, it retransmits the requested fragments if it still has them in its retransmission cache. However, this is a link layer retransmission. It's not an end-to-end retransmission. So the retransmission window should be brief, and that the period of retransmission determines what's known as the link persistence. It's not a perfect reliability mechanism. It's simply there to fill in opportunistically if fragments can be retransmitted that were somehow lost before the link persistence window expires. So that is really what I wanted to talk about today. I want to just say again that there are three interdependent but separable documents. The first is already an IETF routing working group item, and we're calling for adoption of the other two. So again, the simple BGP-based mobile routing system for the aeronautical telecommunications network is ready for IETF routing working group last call. Automatic extended route optimization, we're asking to be adopted as an IETF routing working group item. And transmission of IP packets overlay multi-link network interfaces, again, we're asking to adopt as an IETF routing working group item. And I believe that's the end of my presentation.
Fred, thank you for presenting and really comprehensive overview of the solution. And we would like to open for questions.
So we just want to point out right now the Arrow and the Omni drafts. They were discussed in 6-man, and now they are under ISE, the independent stream.
I see Adrian Farrell on the call. Adrian, would it be fair for me to ask you to say something about the status of these documents?
It would be fair for you to ask. Oh, you were asking. Yeah. So after some back and forth in history, Fred brought these documents to me as independent stream editor because I think it's fair to say he was finding it hard to get traction in the IETF. And that makes the independent stream a potential publication venue. After a certain amount of work and polishing and more discussion, this time round it looks like with presentations in the internet area and Rtgwg, there is again an option for taking the work to the IETF. As independent stream editor, I like it when the IETF works on things that are in scope for the IETF and the community wants to work on them. I prefer that to publishing them in the independent stream, but that doesn't mean that I'm slamming any doors. The documents at the moment are flagged as being in the independent stream, and that's purely just because that's how they are in the data tracker. I could turn off that flag at any time, and certainly if a working group shows that it wants to talk about it, not necessarily adopt yet, but at least talk about the work, then that would be the appropriate thing to do. I hope that's clear.
Thank you, Adrian.
So,
Any other questions, comments?
the Omni draft needs a change in IPv6 packet. So that one certainly needs to be discussed in 6-man. The change to the IPv6 packet at that level doesn't belong to Rtgwg. That's one of the issues I see.
When you say changes to the IPv6 packet, are you referring to the new Omni option? Is that the piece that you're asking about?
Yeah. So
Okay.
yeah.
More from a kind of process perspective, those are large documents, and in order to progress them in routing, we really need to see willingness of working group to participate in discussion, looking into it, and at least from what I gather from people here on the meeting, I don't really see significant interest in progressing in routing. Obviously, we will poll mailing list because not everybody who is participating in routing is here. But practically, interest of people to work on it would be pre-requirement to progress document in Rtgwg. That's what I see now, at least.
Linda, you want to say something?
Question. These presentations are very interesting, showing different ways of doing overlay network. I'm just curious, what impact does it have to the existing routing protocol? Does it require any interoperability from different vendors in the routing domain?
The routing protocol that's used in the Omni overlay is BGP, However, it's a separate BGP instance that does not interact with the internet BGP routing system in any way. It's its own overlay instance. And it's working based on IPv6 prefixes using standard IPv6 routing. So there's not really any changes to routing protocols. And then any interdomain routing protocols, your OSPFs or RIP or whatever might happen to be there, operate as they always have, and Omni Arrow don't interact with those in any way.
So the BGP running among those Omni nodes are separate instance from the underlay, right? So is any protocol extension needed to run this overlay BGP slices or instances?
No, in fact, I've got this set up in a in demonstration networks where I'm using standard Quagga routing, Zebra Quagga routing, with no changes whatsoever. It simply injects the IPv6 unique local address prefixes into the BGP routing protocol, and standard BGP routing is used.
Okay, thank you.
So since there's no more questions, I think we'll take it to the list and discuss it among participants in routing working group, as well as probably with Adrian, and we'll take it from there. Thank you, Fred, again.
Thank you for the time.
Xuesong, you are the next. You want to do the slides share yourself, or I can do it for you?
Could you please share the screen? Thank you. Thank you. This is Xuesong, and from Huawei, I will introduce our work about SRv6 midpoint protection. Next slide, please. Actually, we have introduced this work in RTG for several times, so I think most of people will be familiar with this work. I won't go to details about the motivations and goals again. Basically, this document introduces SRv6 midpoint protection mechanisms. When a SRv6 endpoint fails, an SRv6 proxy forwarding node can replace the segment of the failed endpoint to the next segment to provide local protection for the endpoint. And next slide, please. In this version, we divided the SRv6 midpoint protection mechanisms into two periods. In the first period, before IGP convergence, the repair node finds that the neighbor has failed, and the neighbor is an endpoint. So it will perform the proxy forwarding and send packet to the next available endpoint in the segment list. In the second period, after IGP convergence, any upstream node that has been converged and deleted the FIP to the failed node will be the repair node and perform the proxy forwarding. After the SRv6 policy convergence, another converged path will be selected to translate the packet. Next slide, please. In the document, we specifies the SRv6 midpoint protection behavior. In some cases, it's divided about when to trigger the behavior, but the behavior itself is similar. The segment left decreases, updates the IPv6 destination address with the SRH segment left in that case, and the FIB lookup on the updated destination address forward packet according to the matched entry. That is the behavior. Next slide, please. Here is a very brief overview of the history of the draft. In the first two versions, the mechanisms is defined. And in the second, in the version 02, we update section 6 and the security consideration, and specifies that the SRv6 midpoint protection can only be excluded when the repair node and the failed endpoint are in the same SRv6 domain. And in version 03, we update section 5 according to the discussion in the mailing list of Spring Working Group, and explains that in some use cases, the endpoint can't be bypassed. And maybe some other document will help to handle this case. And in the last two versions, version 04 and version 05, we modified the test and add a new core order. Thank you. Thank you for the contribution of the new core order from China Mobile. Next page, please. Actually, in this IETF, we think the document is stable and has been fully discussed. And based on the suggestion of the working group in last IETF, we bring the work to Spring Working Group. And we have collected some feedback in Spring Working Group. Here are the discussions on Monday in the session of Spring. The first one is how to deal with the case that when the segment of the next endpoint is also failed. Actually, the process can be iterated. There will be another repair node that's the proxy forwarding to skip the second failed node until the reachable endpoint is selected or the segment is last in the segment list. Another question from the working group is why a local repair solution is requested when the end-to-end protection could solve the problem. We believe that the repair solution could provide faster protection mechanisms than the end-to-end solution. And in some cases, this is requested. And another question from Spring is when the repair node is a transit node, it may be against RFC 8200, which won't allow the transit node to modify SRH. To solve this problem, we have sent an email to 6-man mailing list. And also, actually, the section 6 security considerations, as I have mentioned before, is trying to solve the problem. And we propose to check that the skipped segment belongs to the same block as the repair node first, to guarantee that they are in the same trusted domain before doing the proxy forwarding defined in this document. So we think the transit node is could be trusted in this case. And after all the modification and work and discussions, we think this document is ready for working group adoption. And we would like also see the comments or questions from RTG. Okay, that's all.
Keaton, go ahead.
Ketan Taravlikar, Cisco. What's the dependency of this draft against the proxy forwarding draft for midpoint protection?
These two documents are independent. The other document is about the IGP extensions to make some upstream nodes to do the proxy forwarding. But this document is defining the behavior of proxy forwarding in SRv6. So these are two independent documents.
So does this draft require the extensions in the proxy forwarding draft?
Not
Because
really, but
the presentation talked about proxy forwarding, and the co-authors seem to be the same. So I'm trying to understand.
I understand you. You think that because it is mentioned that proxy forwarding in both documents, but actually the contents of and scope of these two documents are totally different. The first document you mentioned is to actually advertise the capability of some nodes that could do the proxy forwarding. But this document is defines the how to do the proxy forwarding. So with the first document, it will help to make this document work. But without that, it still work. This is independent work.
Okay, a follow-up, quick follow-up. So is this draft kind of equivalent to the Spring Working Group draft of SRT segment protection?
Yes, kind of. That document solved the problem in SRMPS network, and this document defines the similar mechanisms in an SRv6 network.
Okay. But the, I mean, but I think the proxy forwarding proposal, so it would help if you could clarify these perhaps in the draft, because the same authors are saying that the version which is adopted is not good or okay, and there is a proposal for proxy forwarding base being a better mechanism. But here we have a proposal which says there is no need for proxy forwarding. So it's just a bit confusing. If you could maybe clarify that, it would help. Thank you.
Okay, we could add some tests to clarify the relationship. Thank you. Thank you for your comments.
We've got 2 people in the queue. Ashik?
Just getting ready for the next one. I don't have any questions. Maybe the next
Bama?
Yeah. So I think the one in the Spring Group is mostly focused on the SR MPLS, but this one is focused on SRv6. So that's the one. That's the major difference.
Whoever puts it in, but they're trying to solve the same problem, right? So
Yeah, the same problem but different domain. But that one focus on the SR MPLS, but this one focus on IP SRv6.
okay, I think we can take it further on the list.
Yeah, okay.
But it would be good to clarify. This can be clarified because
Yeah.
it's the same
Yeah,
co-authors on both.
Yeah, you're right. Thank you.
Yeah, and it's still up to chairs, and we are in discussion with Spring chairs where to keep fast convergence documents, how to progress them together, because, I mean, from formally, it doesn't make sense to keep a SRv6 in one place while MPLS another, while talking about same technology, right? So I agree with Kate's comments. It really needs to be clearly specified documents about interdependency, but practically it's on our side to talk with Spring shares, potentially with Alvaro and Martin, and see how we progress further. There's probably 5 or 6 different documents trying to do similar things.
So Jeff, if I understand this right, we still supposed to wait for the results of the discussion to
yeah. So independently of yes, independently of where we decide to keep the documents, please do progress on enhancing them, making them better, technically more readable, and so forth. So IETF work doesn't stop. It's more from the organization perspective, how we progress at this routing area.
Yeah. Also, Xuesong, please make sure you send an email to discuss in the working group about this draft, the header part.
Yes, I have sent an email to 6man. I think Spring is also CC'd. Last time I will also CC Rtgwg.
Yeah. Okay, that would be good. Thank you.
because the problem of the working group discussion has lasted for several meetings, last one and the one before last one. So we think this is not the reason to just stop the progress of this document. If people think the document is reasonable and this document has already been discussed in spring already, I think no matter which working group it should belong, we can consider to adopt the document if we think the mechanisms is reasonable and the comments from people have already been addressed. So what do you think? Because the working group discussion, the home of the document has already been discussed for several times.
Well, I think we need to figure out with Spring One exactly where to put the mechanism, right? So like Jeff already mentioned, if the MPRS solution is in Spring, if it's the same mechanism, I also feel this should be together, not one in RTGWG and the other in Spring. But we can resolve this offline on the list.
Okay. Looking forward to the results.
So the ball is in our court, and we'll work on it.
Okay, thank you.
Actually, we already are.
Yeah, sure.
So if no more questions, we go to the next presenter. Kosik, you want to try to present yourself?
Yes, let me try. Yeah.
Yeah, I grant you the. Cool. Good.
Can you see my slide?
Yes.
Okay, thank you.
Go ahead.
Okay. So hello everyone. Good afternoon, good morning, or good evening, based on wherever you are. I'm going to present the extension of transport network our mobility in the data network on behalf of the other authors. Just a quick recap from IETF 109 and the background. So this draft was originally presented in the IETF 109. As a quick background, the existing transport network our mobility for 5G defines a framework for mapping that 5G mobile systems, slice and service types to the corresponding underlying paths. But the focus of that work is limited in the mobility domain. So now to maintain that end-to-end network characteristics, the framework needs to be expanded beyond the UPF in the data network. So this proposed draft kind of defines a framework for extending that mobility our transport network characteristics from the UPF to the data network. So the figure below kind of represents that. Like the left-hand side, we see the mobility network is represented by the TNR mobility draft, and where the right-hand side is represented by this proposed draft. Just a quick note, after IETF 109, we received some good feedback and suggestions, and we expanded based on that feedback. Thanks, Jeff and Dhruv, for reviewing it offline and providing that valuable recommendation. The next slide on the packet transitions from mobile network to the data network. There are two scenarios exist here. The first scenario is the UPF is part of the HCP node. And in that case, local policy could be configured in the node itself, where that mobility SST UDP source port could be transferred to the local CPE node. So that's the first scenario. The second scenario, in the UPF and the HCP node are connected through an IP network. And in that case, also a local policy could be configured, and the UDP source port carried by the original UDP header in the mobile network that can be transferred over some transport header based on the operator choice in the CPE node. So either one of these kind of approaches in a data plane way method, we transfer the transport characteristics in the data network. Now, once we transfer the network characteristics in the data network, the next mechanism comes, like how it would be mapped in that using a different mechanism to maintain that same characteristics. So there are different scenarios and different mechanism for that. The first three scenarios we already discussed in the earlier IETF. It's a BGP SRT controller driven approach. The first scenario. The second is the ODN SRT policy based approach, and the third is same SRT controller over REST conf and gRPC session, and that will be providing the mapping. And the fourth one is a new addition to the flow spec controller, and that kind of use the mapping using the indirection ID technique. So we'll go over it. So the next, again, just a quick recap from that 109, the BGP SRT policy for 10-hour mobility. The way it works, the ingress node will have a BGP SR policy session with the SRT controller, and the controller would be provisioned for the different SST specific source port range and the corresponding TE policies and the binding seed. Those would be downloaded by the SRT policy NLRI and sub-TLVs, along with a 5G metadata sub-TLV, which we introduced last time, that carries the UDP source port range. Now, when the packet comes from the UE side to the ingress node, and using one of the technique that's kind of the characteristics is transferred, the source port, UDP source port, if it falls within that UDP source port range, the corresponding SR policy would be applied to maintain that characteristics. It would be redirected to one of that path, like for URLLC traffic. If the source port comes with a URLLC range and it's mapped to that policy path, it would be redirected to maybe HDC. For MIOT, could be as shown in the specific policy, could redirect to a public cloud, or EMBB, it would be private DC. So here is the kind of it will use the BGP SRT policy for the mapping. If there is no binding seed or the policy found for a specific source port, then it will take a best effort path. Just a quick note here, there is a existing draft in IDR for edge compute app metadata, where we see the egress side edge compute server belong to certain LDN. They try to propagate over BGP some app metadata sub-TLV, and that's get propagated over a RR through the controller to the ingress node to take a best path to the reach to the different egress edge server. So there is a future possibility those sub-TLVs could be propagated part of the 5G metadata sub-TLV. It's just that's why it's just capturing the option here. The next one, it shows that the new addition, like a BGP flow spec traffic redirect for 10-hour mobility. Here again, the controller is flow spec controller having a session, flow spec sessions with the ingress node. And again, the controller is provisioned with a different UDP source port range corresponding to the different SSTs. And with that corresponding mapping is the here generalized indirection ID. So the flow spec in LRI would be downloading the UDP source port range to the ingress node, along with the action for the extended action for the indirection ID in the extended community. So now when the packet comes from the ingress in the ingress node from the UE side based on the, again, the source port would match, try to match within that the source port range, which is downloaded by the prospect controller, and map to a certain indirection ID, and that could be a map to maybe a specific binding set that would be redirected to a specific policy, which will be mapped to a transport header and take it to that one of the path, URLLC, MIOT, or EMBB, as we kind of see it here. Just a note here, again, there is a new draft is proposed in the IDR that would be presented in Friday. So if there is a more granular flow, then the traffic redirections will be happen based on whatever is described in the IDR flow spec in our mobility draft. So here we are covering that specific SST range, and it's kind of a, as long as the UDP source port belongs to that certain range, like it would be redirected based on the flow spec. So it's kind of, in a way, it gives our operator good choices among all the methods kind of there. The way you try to map in the ingress node, either flow spec or BGP SRT policy, or SRT ODN driven approach, or even the gRPC netconf with a SRT controller. So I'm not going all the approaches because it's kind of those are there is no change on those from the previous presentations. Next part is the extending that transport network, our network characteristics for the SD-WAN network. And the SD-WAN network is presented here based on the BGP SD-WAN use case draft. There are CPE node, and the two CPE nodes are presented, and it's in the case of hybrid SD-WAN scenarios, there would be IPsec SA tunnel between the nodes, and there would be also maybe low latency path using a MPLS over GRE. This is a hybrid SD-WAN scenarios. The endpoints are auto-discovered using the RR controller. And in the enterprise 5G use case, if you see that CUE could be kind of traffic could be landing into that CPE node. Here, the DMM draft is expanded to cover the security characteristics under each SST. So the subrange is allocated under each SST to have the security characteristics. So when that kind of UE traffic comes to the SD-WAN CP edge node, that's based on the security characteristics, it's given a priority. It would be mapped to a certain IPsec SA tunnel between the branch-to-branch communication, because in the SD-WAN deployment, the security takes a priority, and generally they have the IPsec tunnels. If we see any traffic coming from the UE side, and let's say URLLC traffic without any security characteristics, then if we have a path for, let's say, MPLS over GRE path, that could be redirected over that path. So that's how it will map over a SD-WAN network. But I also kind of want to add a note here that in the specific use case where there is based on the SD-WAN use case drop, private VPN PE based SD-WAN use case, the PE could be kind of initiating the SD-WAN tunnel, and the VPN PEs are connected to RR, and they could have a SD-WAN tunnel. And in that case, like again, besides that connections to the RR controller, they could, the ingress P node could have a connections to that SRT controller. And in that case, that mechanism we saw, the previous mechanism would be applied on top of that security header. We would be applying a SRT mechanism. So that is covered in the draft as well as in the backup slide. So I'm kind of skipping that part for the limited time. And the next slide is basically as a next step, we would be looking for 5G metadata sub TLV, which is defined that IANA code for the type field, comments we have addressed from IETF 109. At this point, kind of request for workgroup adoption, and we'll continue to update based on the feedback. Another quick note I forgot to mention in that in the slide that for the BGP SRPC ODN based integrations, there are new metric types are used. For the metric types are used for the EMBB, URLLC, and MIOT. So that's need to be expanded in the PSEP side. So once the document is adopted, we can plan for expanding those metric type in the PSEP. So that's all pretty much I have, and I can, if you have questions, I can try to address here.
There has been a number of questions on the chat. Edward, would you want to read them aloud?
I'm not sure that it may be my problem. I have not understood on slide 6 why it's about UDP source port, because okay, if it's UDP, why not TCP? If it's a subscriber or traffic identification, why it's not TEID from GTP? Maybe I just don't know properly 5G.
Okay, so basically, it was like if you see there is a, let me go back to this. So if you look into this, there is a existing draft in the DMM, and that's basically trying to define the different slice and service types, like for the MIOT and EMBB and URLLC, and that's kind of allocated. There is a table there if you look into the draft. So that allocates a different UDP source port range for different SSTs, and from when the traffic generally, and that's how they kind of try to maintain that specific using that UDP source port range to maintain the characteristics in the mobile network. They understand it's for MIOT or it kind of a EMBB or URLLC. Now that range is basically carried over UDP source port, and that's basically dictates the network characteristics what is maintained in the mobile network. So now that's what we are trying to carry in the data network to maintain. That's the only informations you can bring it pretty much from the GTP side or the mobile side of the network to the in the data network to maintain kind of a end-to-end UE network characteristics. So that's why we are not kind of adding any extra field. It is whatever it is coming and whatever it is defined based on the IETF DMM draft, and that's what we are kind of extending and kind of trying to maintain the same characteristics.
But this draft looks like from IETF, probably because it's related to base station. Probably it should be on 3GPP side. Probably it should be some draft, or do they have acceptance from 3GPP? Because you're asking effectively special functionality from BNG, from base node, from eNode B. But it's 3GPP stuff. It's not IETF.
No, so the drop is accepted. Let me go back to the previous slide. So the drop is accepted in the DMM. So only information it's carrying. I wish, that we had that the SST range, but the only information is carrying is that in the UDP header. It's nothing we are bringing from the GTP header or anything from the UE specific. So only informations we are bringing here that there is a UDP source port, which is kind of given for a specific SST range. So that informations we are bringing to the transport header. I don't think that's depends on the 3GPP because that's a UDP header kind of dictates the network characteristics in the mobile network, and that information we are bringing in a loosely coupled way to the data network side.
Okay. I would advise you to send an email to the working group mailing list to discuss in more details, and we've got G next in the line.
Okay.
G?
My comments is similar. I think the pre-assumption is that the UDP source port will be used to identify the 3GPP slice and service type. I guess this is described in the DMMM document. Well,
correct.
Perhaps the 3GPP, is there any opinion from the 3GPP side to use what kind of which fields in the package to map to the service and slice or service types? Is there any feedback? Right?
Yeah, so G, if you see that we are not kind of directly bringing the GTPU header, like just we are not propagating that. It's like obviously if it is a TID or some kind of informations from the GTPU header, that we cannot propagate. That's the kind of context where we are not proposing to bring into the data network. We are all just bringing kind of that's UDP header, the source port, and kind of even not even saying that's the same header would be carried, right? Like any type of transport header, it can be carried into the data network side. So I think means in terms of means the I don't know whether Uma is there, but like I think we have internally reviewed. I don't see that's any issue causing any issues from the 3GPP side. Linda, if you are here, do you want to comment on that?
Yeah, I just want to add a few comments. Actually, I wrote that on the chat window. So basically, the GTP tunnel head is UDP based. And there are a couple of ways for the 5G to propagate some of the information to the local data network. So supposedly, like there's be a controller, they could have informed our IP network outside UTF, the UDP ports being used by the GTP tunnel. That's one method. And another method is when the traffic comes to the ingress node, our CPE node, and between the CPE node to the edge, the data center, there could be another layer of transport header. And that transport header could continue using a similar port range as used by the 5G to ensure the end-to-end quality of the service. So with that, we could also reuse some of the UDP ports being used within the mobile network, just on different header. Instead of on GTP header, a tunnel header is used on another layer of transport header. Here we just say transport, we don't specifically say which header it is here.
Okay, my understanding is this may be one option for the mapping from the 3GPP slice services to the transport, where it requires some coordination from the mobile side, so that it will use this UDP source port range for specific service or slice. So maybe
right.
this can be just one option.
Yeah.
Yeah.
It is an option, and now without share head-on, in 3G and 4G networks, this option had been used extensively. If we look 10, 12 years back, it has been deployed this way in a lot of different places. So it's not really a new way of doing it. So you just copy, you use UDP source port in GDP encapsulation to derive intent with regards to treatment in the IP network. We've got Chengli. Please go ahead.
The first one is, does the work define a set of mapping between the mobile network to the, I'll say, data network resources, right?
Correct.
Okay.
Is this what
the second one is?
Huh?
Yeah. The second one is it any implementation yet?
So second one, what is the question? Chen?
Is there any implementation already?
Oh, okay. So no, currently I don't think we have a implementations ready. it's kind of giving a different choices to the operator, like based on the network deployment, we can pick one of the mechanism, but the currently I don't think we have a implementations yet. Yeah.
Thank you.
And AC.
Kind of all over there. There's like 4 different options for for doing this. Kind of the same as my comments, similar to Chen's, and sort of a new one, the flow spec controller. I guess it was inevitable. I guess this is what flow spec v2 was going to be. It's going to be open flow at layer 3. What is, other than the overlap of authors, what is the tie-in to SD-WAN? Just that there could be different, could be requirement. I mean, it doesn't look like it's handled any different than any other app-aware, you know, any app-aware flows. It doesn't appear to me that 5G should be any different than any other ones that are in back of an SD-WAN or run over an SD-WAN overlay.
Right.
So there's significant overlap of offers, so it's tempting to reference your own documents. But what is the real reason for that?
Yeah. So let me go a little more AC on that. So yeah, there are 4 mechanisms. We kind of kept it because it's first. Your first questions regarding what kind of along the line what Chen mentioned, it's kind of gives an option to the operator. That way, like based on the deployment, they can choose one of the mechanism to maintain the characteristics. So we are not kind of strictly suggesting go by one particular mechanism. So probably that's kind of gives a better choice. That's our view. Now coming back to the SD-WAN network, like if we see that any SD-WAN based on the SD-WAN use case draft and the deployment scenarios, especially in the SD-WAN network, in a hybrid SD-WAN, there would be kind of some secure tunnels and some MPLS over GRE link could be between the two branch-to-branch communications, right? And in that case, the main important thing is that secure communications between the branch or the cloud gateway. And if we now if it's UE traffic kind of land in the one of the CPE node, and then how do we maintain the security characteristics if we other than kind of a mapping to specific SRT mechanism? If the security is a priority, so then that has to be given a choice. So that's one of the reasons that dropped the other DML.
Okay, but that applies to every application. That applies to every application, actually, just about.
Agreed, AC, but kind of for SD-WAN case, it is pretty obvious, like between the branch-to-branch traffic, you need to have a security. And all are kind of saying that if there is a security characteristics comes on a specific traffic from the UE, so that would be given a priority to map to a specific IPsec tunnel. Otherwise, it could be mapped to a any URL traffic. And in this case, this is basically if you see the SD-WAN deployment, in some cases there are really CE node kind of there are 2 sets of deployment scenarios. One is the hybrid SD-WAN. This is
we don't need it. We've already had the tutorial on that. I understand SD-WAN very well. I was just saying it's not really this application isn't any different than any other.
Mm-hmm.
Or that's what I was wondering why there was a specific session on that. Okay.
Okay. So for the flow stack, There's current flow spec for redirect to IP tunnel and SRv6 tunnel, SRv6 path. And the flow spec addition is to add another type of tunnels, which is IPsec Security Association tunnel. So that's how like SD1 been using that special additional flow spec.
I think we'll cut the queue here. Practically to the authors, I think it would be good to extend the draft to explain the mapping, probably even starting with Q5 4G towards 5QI in 5G, and how all of this maps and how QoS architecture end-to-end would look like. It would make understanding of the draft much better. I see the questions are exactly because the mapping is not well understood, and I agree that 3GPP part is rather important here.
Okay, so we'll take it to the list, and maybe we'll try to expand based on the comments. So please feel free to post comments. I will initiate a thread, and please feel free to post comments. We'll try to expand based on that. We'll expand the draft accordingly.
And perhaps include reference informative to TS 23501, which is the QoS architecture in 5G.
Okay. Yes, sure. Jeff will capture those references.
Thank you for the presentation, and let's
Thank you.
on. Thank you. Daniel?
And because just actually a tiny update of my slides, so I'd like to share my screen by myself.
Absolutely, go ahead.
Okay. Is my screen available for everyone?
It's coming.
Yeah.
Okay.
I think there are a few buttons you need to grant access to your screen. You need to confirm.
Confirm. Okay, sorry. Oh, sorry. Is it now okay?
Now we see your browser. Yeah.
Okay. This is Daniel Huang, and it's my pleasure to make the presentation of the drafts on behalf of the authors. And
sorry for interrupting you. We see your browser, not your slides.
Excuse me. So. I'm trying to figure out what's.
Again, your browser.
I'll try again. I suppose this time is okay.
Yeah.
Okay.
Please go into presentation mode.
Okay. The draft is about computing delivery in routing network. Actually, what the computing delivery means is might be confused for someone in the community. So I would like to clarify in the next couple of slides.
Let's try to move
And
PowerPoint into presentation mode. Now you're just viewing the slides.
okay.
Now we are still seeing the editor mode.
I'm in the full screen mode.
No,
Not
you should
from
try
what we see.
presentation mode. Click the arrow button, the orange arrow button at the bottom.
Yeah, that's one.
Okay. Actually, about computing delivering routing network is not a new topic in this community, because there's during the past 2 years, there's a couple of impressive drafts which have been discussed in the past conferences, the site meetings about this. So there's a lot of use cases, problem statements, different architecture. So the first page of my slides is not exactly the use case. I simply want to clarify the how to say, the general use case and rationale of my proposal. When it comes to the centralized computing deployment, the sensing and the scheduling of the computing services and resources by the application system makes more sense than being done by the routing network. And while the coordination between the cloud services and resources and networking, I mean route networking, could be cost effective because of the scalability and the intensity under the centralized computing deployment mode. And so as far as the centralized computing deployment, the use case stays perfectly within the computing unaware routing architecture as the routing mechanism right now works. So when it however, when it comes to distributed computing deployment mode, the interconnection among particularly among the edge computing size is in a different shape. And as in the use case drops that I've mentioned, illustrate there's a strong motivation to coordinate the computing services and resources among the distributed nodes, and then make them as to the kind of the virtualized the computing pool to bring benefits to a lot of applications and services and use cases. So that's the comparison between the two computing deployment modes. Just why we proposed a new framework about computing delivery and the routing network. As far as the challenges, problems are concerned, because the routing is actually an inherently addressing system in terms of networking topology, and decoupled from the applications in the cloud. And while routing without aggregation is an important and an indispensable feature of the routing. Nevertheless, the computing resources services has been deployed in such a way that it could not be easily aggregated as the network resources. So, and in the computing interconnection and the coordination is the application level, as as the practice of the ongoing industry lacks the fine-grained network surfaces. That's the summarization of the problems of this. And when it comes to challenges, because full granularity computing services and the resources to stairs in a routing network would be absolutely a disaster. While the computing parameters upon the routing process could incur an unacceptable price. So routing in terms of computing is in a different scenario, which the original routing mechanism is not designed to address. So when it comes to the computing delivery in the routing network mechanism, so the computer status in the routing network has to be put in an engineeringly acceptable way. So the second requirement about this is the computing routing mechanism has to be decoupled from an ongoing routing network. So the would-be framework of the computing delivery could be compatible with the traditional IP and routing network. And also select and limit the routing loads to the computing as well, while the rest should remain as to the all, and which is computing unaware. So the first part of the framework of computing delivery in the routing network is the aggregation of computing services and resources. So we categorize generally the computing resources into two types. One is the global computing routing nodes, where the general computing resource and service layers from the remote computing sites.
Sorry to interrupt, Daniel. We are still seeing your second slide on your screen. Are you still talking to the second slide?
Second slide.
Your slide is now moving. And we are now seeing the presentation mode, we are seeing the editing mode. If you have multiple screens,
this is because it's not multiple screens usually. It's because he's sharing an application and then PowerPoint shares the wrong window.
Okay. What if I return from the presentation mode? What about right now?
You are seeing presentation mode yourself?
Yes, actually.
We are seeing editing mode.
Right. Again, when you share application, it shows the wrong window.
Yeah, you have to share your screen.
Do you want us to share instead?
Okay, to save the time, Injun, would you please share the screen for me? Because I'm not sure.
So maybe I can share your old slides if the changes is not that much.
Yeah. Not so much. It's simply the title, name of the titles has been updated once. The page 4.
So you are at page 4 now?
Yes.
Okay, go ahead.
Okay, thank you. But I do not see the full screen of. I cannot see the two squares and the button somehow.
Yeah, it cuts the 10% of the screen, the button.
See the grey bar near the top to the left of the presentation. Click on the toggle zoom button.
Oh yeah.
Better now?
I still cannot see the full screen. I can only see the figure and about 30% of the squirrel.
All the people watching have to click on that button. It's not a presentation thing, it's a view thing.
For me, I can see the picture and the two text box.
I see the box where I see the picture slide very well when Jim presented aggregation of
Yeah, so everybody has to click on toggle zoom.
Okay, actually I can scroll down by myself. Sorry. Okay. May I continue?
Yeah, go ahead.
Yes, please.
Yeah.
Okay. Sorry. The first part of the framework proposal of our draft is the aggregation of computing services and resources. We categorize the routing node into two types. The first one is I would like to call it the global computing routing nodes, where the general computing resource and service data from the remote computing sites will be maintained. And the global computing status is categorized to be as comparatively stable as possible, such as the overall GPU and CPU occupation rate and the computing services types that are available in the specific computing sites. And when it comes to local computing routing nodes, simply the dynamic computing service, such as the instances, some computing instances or virtual machine, the host, something like that, status from the local computing sites to be maintained at the local sites, which always would be the egress node. So next, please. Okay. The second part of the proposal is about the what you call the two-segment routing forwarding, according to the two the two routing nodes in the previous slides, as the previous slide indicates. The first segment, we call it the global computing routing segment. Actually, is simply from ingress to egress, such as illustrated in this figure. R1 as ingress will select the egress in terms of the global computing status, maintained the edge at R1 as demonstrated in the previous slide, and an inbound encapsulation of computing service and resources is delivered to the egress and an overlay tunnel. And traffic affinity is guaranteed by combining the 5 tuples and the egress. When it comes to the another routing segment, we call it the local computing routing segment. Through the inbound computing service and resource encapsulation and the local computing status, a specific service instance such as a host and a virtual machine will be selected at R2, which is supposed to be the egress of the entire network domain. Also, the traffic affinity is again guaranteed by combining the 5 tuples and the service host. Now, next, please. Okay. This is the workflow about the computing service resources aggregation. a full granularity computing service resource status is notified from the cloud sites to the local edge loads, edge networking loads, which would maintain the local computing status while update to the global part to the remote networking nodes. The global computing status update to domain actually overlaps to its. Sorry? Oh, okay. Overlaps with the traditional routing network domain. The compute so the computing routing table size thus would be reduced, and the update frequency will reside in the controlled and acceptable range. Next, please.
Please try to finish with a minute or two. We are over time.
Okay. Okay. Thank you. When it comes to control plane and data plane, we have three general options. One, global computing status declared the maintains the controller, which delivers the routing policy from ingress to egress. But local computing status should be better maintained the egress locally. As far as to the distributed control plane, global computing status only is to propagate among edge loads by routing protocol, while local computing status could be notified through ways beyond the routing protocols. A hybrid actually is the combination of the two control mode. Next, please. Because both the global and local computing status information are updated and integrated into the routing network process as the third-party resources. So the security and credibility of the computing service and resource have to be guaranteed and addressed. Details of security and credibility consideration will be either proposed in the future updated version of this draft, or will be proposed in the standalone draft. Next, please. And a trial test based on our prototype system is ongoing and in good progress. And the result will be synced with the group as soon as possible. That's all of my presentation. Thanks very much for your time.
Thank you very much for presenting. As you know, Rtgwg is looking into network computing, so I would advise you to engage and present there as well. And thank you for the presentation, and to our esteemed attendees, we hope to see you tomorrow, second meeting. Thanks, everyone.
Thank you.
Thank you. Hey, we did really well, and I still feel ashamed not remembering that it's the first time you're the co-chair, not the second. I was sure that we did it like last IETF. You didn't receive